All right, so we are glad to have Professor Thadhani here today, who's a professor at Georgia Tech, and he joined the Georgia Tech faculty back in 1992, so a number of years. And previous to that, he worked for Center for Explosive Technology at New Mexico Tech, and also he worked at Caltech. He has a background in metallurgical engineering, and his research focuses on metallurgy, which of high pressure, shock induced physical, chemical, and mechanical changes and deformation, fracture response of metals, ceramics, polymers, and composites. So basically all types of materials. And predominantly he investigates the ballistic impact and the high strain rates. So that's also a topic which is of great interest at ASU. A number of faculty work on that area. So he has advised 15 visiting scientists, postdocs, 33 PhDs, so a whooping number, and 19 MS degree students, and mentored about 100 undergrad researchers. He has obtained almost 18 million in funding, and he is also a recipient of the TMS Leadership Award. He's a fellow of the ASM International, APS, and the Academy of Euro-Mediterranean Academy of Arts and Sciences. So we are glad to have you here. Thanks for accepting our invite. The floor is all yours.
Thank you, Ankit, for that kind invitation. I'm delighted to be in Arizona virtually to give this seminar, and I really appreciate the opportunity. So even though my background is metallurgical engineering, as Ankit, you mentioned, my work is focused primarily on looking at the effects of high pressure shock compression on different materials. And today I'm actually going to talk about, about the use of a new technique, essentially X-ray phase contrast imaging for probing materials under these high pressure environments. This is not going to be a metallic component, but it's actually going to be a polymer composite that's filled with a high loading density of solid particles. Okay, so let's start by first looking at why are we interested in this. Okay, and I show a picture of the Meteorite Crater that's near Flagstaff, Arizona, I think very close to where you all are. Okay, and I think an interesting observation here is obviously you clearly see the crater that has been produced when the meteorite hit the Earth's crust. But interesting enough, that impact generated shock waves, and those shock waves also turns out that result in all kinds of chemical changes, physical changes, and mechanical changes. Okay, and that's the interest area that I have, to essentially look at at what those mechanical changes are. For example, not only you have a crater here, there's a lot of fragmentation of rock that, as you can imagine, may have happened, as well as the consolidation of soil that may have happened. Okay, physical changes. There are materials that go through phase transformations or new chemistries. Turns out that in one of the examples of a meteorite crater, the nickel from the meteorite combined with the iron from the Earth's crust to form a new compound of iron and nickel. Okay, so there are many such observations of such changes that take place in materials under these conditions, and that's what is of interest to me. Okay, now, of course, you cannot wait for meteorites to fall to do these type of studies, so you have to have your own lab where you can perform such experiments, and we have a great facility with different types of gas guns, as well as a laser launching mechanism for thin foils, a variety of diagnostics, multiplex velocimetry probes, or Pdb, VISAR, high-speed imaging techniques, new types of sensors that we are developing as well, and also, various levels of numerical simulations that we perform, both for the purpose of validation of models, so that we can combine those with experimental observations, as well as look at what's going on inside the material. Okay, so that's the capability that we have, and the overall theme of and the breadth of the work that I'm looking at, as I mentioned, we have a lot of interest in studying phase transformations. And this is an example of where we are interested in looking at the polymorphism in a metallic glass. So a metallic glass, a zirconium-based metallic glass, actually also undergoes phase transition from one ambient pressure phase to a higher density, higher modulus phase. Okay, and the inference of that phase change that we get is based on measurements of pressure versus density. Okay, and when you see that type of an abrupt change in the pressure density profile, that gives us an indication of that phase change. Similarly, chemical reactions, nickel and aluminum can react under high pressure. These are very highly exothermic reactions. And again, on the basis of measurements of stress and relative volume is, or density is not directly measured, but you can calculate that from shock or particle velocity measurements as well. But you plot those in this type of a map, and when you see deviations from what you would otherwise consider under without any changes taking place, those type of deviations are inferences for the chemical reaction or phase change taking place. This is another example of the mechanical behavior where granular materials, even sand, how does sand densify at pressure? Okay, and sand is very interesting because it can be wet, it can be dry, it can also contain a lot of contaminations. Okay, so how does all of that affect the densification behavior of a material such as sand or any type of metallic constituent? Okay, and the same thing applies. How does failure take place in materials under dynamically generated tension or even some extreme strain that can be imparted during impact conditions? So all of these are effects that we study by controlling the loading conditions under uniaxial strain, meaning the strain is propagating in only one direction, or uniaxial stress, meaning the material is being stressed in one direction. Okay, so under those control conditions, we try to investigate these changes that take place in materials using time and spatially resolved measurements. Okay, and how those changes are influenced as a function of microstructure. At the end of the day, that's being a material scientist, that's our interest. How does microstructure influence these changes? Okay, that's the overall work that I do in my group. Now, more specifically for this presentation, let me give you an outline of what I'm going to cover. I'm going to start by talking about, what is a shockwave? And how do we probe the shockwave propagation in materials, particularly those that are highly heterogeneous? Okay, what is this technique of X-ray phase contrast imaging? Of course, this is a technique that utilizes the high energy source, such as the synchrotron at the advanced photon source. And then if you're considering heterogeneous materials, then it turns out that additively manufactured materials have a significant level of heterogeneities that play an obvious role in influencing their behavior. So I'm going to talk about that process in particularly when you're trying to make these high solids loaded polymer composites. What are those characteristics of those heterogeneities? And that's one of the materials that is of interest to us, and that's what I'm going to be talking about. Then how do we did the experiments using the dynamic compression sector at the Argonne National Lab, at the advanced photon source? And what was the specific nature of these experiments? In other words, we use this X-ray phase contrast imaging as like an immaterial probe of the speed at which the shock wave, as well as the particles behind the shock front, are propagating. So at the end of the day, what's the correlation between that shock and particle velocity? And that correlation can again inform us and give us a lot of understanding of the response of materials. Okay. The other thing that we will see is we can also use digital imaging correlation to obtain strain measurements. Okay, and I'll talk about that as well before summarizing and briefly talking about future work. Okay, so what is a shock wave? Okay, and I think a simple way to visualize a shock wave is, if you can imagine a train that is carrying all these containers behind it. What if it is moving at a high speed and hits a very, very sturdy ball or some rigid object? So what will happen? Of course, there will be this collision. The collision will result in these containers, piling up behind each other. And if you were to kind of view from outside to see what is happening, you'll see that these collided containers, there's like a front of those containers that is moving backwards from the impact. So at time T1, just at impact, time T2, you can see there were a couple of containers that have sort of piled back to back. And then at time T3, there are probably about 4 or 5 containers that have been piled up. Okay, so you can visualize this as what has created a shock wave. Shock wave, essentially, it's a disturbance that results in an instantaneous or a discontinuous change in properties. So, for example, ahead of the shock front, these containers are seeing nothing. They are like, cool, nothing has happened to us. But behind that front, the material is in a highly disturbed state. And because this discontinuity is propagating in the form of a wave, you can imagine that this front is moving at a certain speed called the shock velocity, and the particles or the containers behind it have a certain velocity also, and that's defined as a particle velocity. Another way to look at it is, you can imagine a snow plow. A snow plow is piling up the snow ahead of it, and that front of the snow is moving at a certain velocity called the shock speed, and the plow itself, that is moving at a speed called the particle velocity. Okay, and it turns out that the shock and particle velocity describe an equation of state, which is a response of a material, or the high pressure or the shock compression response of the material. Okay, and if nothing really happens in the material, it behaves nominally under ideal conditions. There will be a kind of a linear relationship. However, if there is a phase change or a chemical reaction or a mechanical change, then you will see an abrupt or some discontinuity generated in this linear profile, which would be indicative of the phase change. Now, typically, when you do these measurements, an experimental process like this, where you have an impactor impacting the target, again, you can have stress sensors that are mounted at different locations, stress gauges, or you can do a variety of interferometry that monitors the free surface velocity at the back surface of the sample. Okay, now all of these diagnostics typically give you a volume averaged response, okay, corresponding to whatever is the diameter of the visor or the Pdb beam, the interferometer beam, or the gauge diameter, that is the stress gauge diameter that is monitoring the propagation of the shock wave. Okay, but it doesn't give you an in the material response. Okay, and let me show you a result of like a simulation, of an experiment where the shock was generated upon impact, and you can see that front moving ahead of it, and you can see that taking place. Okay, and you can see the turbulence as well as the heterogeneous nature of the wave front as it is moving. Your diagnostic that we typically use is unable to capture those effects. Okay, although simulations clearly reveal that there are a lot of things happening inside the material, leading to, for example, stress strain localization, which can create hotspots that influence the types of changes that we are interested in monitoring. Okay, and these are really very clearly, revealed by computations, but never really captured by conventional diagnostics. This is where the use of X-ray phase contrast imaging comes in, because it can essentially, allow us to probe inside the material and see and essentially make measurements that are in material, time and spatially resolved measurements. So that's what I'm going to be focusing on in terms of how we have done these measurements and what are the responses that we are capturing. Okay, so just to give you, again, a simple understanding of this X-ray phase contrast imaging, suppose you have a region of a sample, that you're subjecting, you're imposing an X-ray beam, you're shining an X-ray beam, and suppose part of that sample is shocked by shooting an impactor on this sample. So part of it is shocked, and the remaining part is at ambient condition. Remember, that's what I told you earlier, that the shock state is where the high pressure is moving as a front. Ahead of the front, the material is in an ambient condition, and behind it, it's in a high energy, high pressure state. Okay, and there is a sharp interface because obviously there is a significant density difference. Okay, and because of that density difference, you can even have a radiographic, an X-ray radiographic image that will give you that contrast between that high density and the low density region. Okay, in a radiographic image, X-ray radiography setup, it turns out the detector is placed fairly closely to the sample that you are trying to image. However, in phase contrast imaging, turns out that the detector is further away. So the image created now is due to the X-ray absorption and refraction, as well as the Fresnel diffraction that comes from the interaction of that wave as it is propagating through this material, and its interaction produces that additional contrast. So unlike a contrast that you have with X-ray radiographic imaging, you have a significantly better contrast that you can see between different density regions. Okay, and these are examples of detector images of two silica particles. As they have been pushed towards each other, you can see the cracking that is generated in one of the particles here. And in this image, you can see, again, cracking propagating in both of the particles. And due to cracking, there are free surfaces. There are surfaces open up that are low density regions. And that's the reason that you're getting that additional contrast. Okay. So that's what we're going to look at. That's what we're going to use when we impact the material and use this X-ray phase contrast imaging. Can we monitor the shock front and how is it propagating? Okay, and if there are features that are in the material that undergo strain or fracture, what type of information will it give us? Okay, so let me then talk about the material that we investigated. Okay, and I'm sure a lot of you are familiar with the use of additive manufacturing, particularly the use of direct ink-write extrusion, where the ink essentially that is placed in this nozzle, it comes out, is injected, and this material is printed in a line by line, layer by layer, three-dimensional mode, okay, as it is shown in the schematic. The material that we are interested in is a polymer composite, but that contains a very high loading of solid particles. Okay, about 60 to 70% or even higher loading of solid particles. Okay, and just to give you an example of one of those materials that was made in this spiral configuration, if we were to take a CT scan of this material going from the top to the bottom, the picture on this right-hand side shows you, what you observe, like going through slices. Okay, and the particulate nature that you are seeing, okay, the particulate contrast that you are seeing is coming from the presence of those solid particles, and the dark regions that you are seeing are the openings between the different filaments, as you can see along the surface, or even as you go through, the layer by layer, and you can see how those are evolving through the thickness. Okay. If I were to then, consider a section like this and show you, how a two-layer CT cross-section looks like, again, you can see this is the darker opening like that you are seeing. The void is the interlayer region. And again, the particles are also being resolved. Again, this is an object that had probably about 65% solid density of the material. Okay, now if we zoom in further, and I just show you a static shot, okay? So this is like a cross-section of one of these objects. You can see the nature of the cracking, the voids, okay? It's by no means uniform. It's so stochastic, the distribution of these voids, okay? And then if you consider the distribution of the particles, okay? Again, very, very non-uniform. This band that you are seeing is like the interlayer, the space between the two layers, and you can see there are no particles in that region. So those are regions that are deployed of particles, and you can see that even better here. This is like a zoomed in image of one of the matrix areas. So even the matrix actually contains smaller sized particles. So for a material like this, you can imagine how heterogeneous it is. Okay, so what's going to be the shock response for such a material? That's what we are interested in. The specific material that we studied was fabricated in the form of these type of rectangular cubes. Okay, the cubes are essentially 5 centimeter by 4 centimeter by about 1 to 1 centimeter thickness. Okay. And these contain two different types of melamine particles, 30 micron and 10 micron. They also contain glass beads that are about 100 micron. And then geotex. The geotex is these crystalline high contrast particles that you see coming in and out of the CD image. Okay, those are about 100 micron size. And then the methacrylate binder is about 26%. So the total solid volume content is about 74%, and the polymer volume content is about 26%. The void fraction, if you look at the macro scale, it's only about 0.5%. But if you zoom in at these high magnification, and if you take snapshots of these images, then the porosity content shows up a little higher, about 3% or so. Okay. This image on the left-hand side shows you a CT of this entire block, okay? And it kind of gives you the directionality of the voids, okay? So considering the directionality of the voids, as well as the varying aspect ratio, what we were interested in was what if we machined out rectangular cross-sections out of this block, but in different orientations? Meaning along the print direction, which would be the Y direction, perpendicular to the print direction, which would be the X direction, okay, and then in the direction of the growth, which would be the Z direction, okay. And we machined out strips that were of the order of 2 millimeter by 3 millimeter by 6 millimeter cross sections, okay. I'm showing you these strips in these schematics here, okay. You can again see 2 millimeters is this thickness. They're 6 millimeter long, and they're about 3 millimeters height. Okay, and we machine these from different orientations. So in one, in this A schematic here, it shows that the impact is actually going to be along that print direction, and we just label it as 100 direction. Okay, in this situation, again, we machined it such that the impact would now be to 90 degrees to the print direction, as it is shown, based on the contours of the individual layers. And finally, this was machined such that the sections are going to come out whereby the impact is going to be along 45 degrees to the print direction. Okay, so upon impact, the shock wave will travel this 6 millimeter length of the material. Okay, it turns out that the X-ray field of view is about 2 millimeters by 2 millimeters. So even though the shock is traveling through a longer distance, this is the region that we are going to be viewing. Okay, and it turns out that the X-ray is going to go into the screen here, meaning it's going to be probing a 2 millimeter thickness of the sample. Okay, so that's how the setup was. Okay, and the whole idea is to generate images and go inside the material, see if we can observe the propagating front, and monitor the speed at which both the front is propagating, that would be the shock velocity, and the speed at which the particles are in motion, which would be the particle velocity, and also see if we can capture the local strain using DIC analysis. Okay, so this is the synchrotron source at the Advanced Photon Source at Argonne National Laboratory. This is where there is a high energy, high brightness X-ray beams that are necessary for doing the X-ray phase contrast imaging. And there is the dynamic compression sector, which is shown here, which has a range of gas guns, a laser flyer setup, as well as explosive chambers. And that's the setup that we use for doing our experiments. Okay, let me show you the experimental setup, or the schematic of the experimental setup. There's a particular gun here called the impulse gun that is about a half-inch diameter, barrel diameter, and that can be used with either powder or gas to launch the projectile. And 23.5 keV X-ray white current beam is imaged on 4 ICCD cameras, and these X-ray bunches arrive every 153.4 nanoseconds. So the sample that I talked to you about, that's a rectangular strip, is mounted in epoxy such that the sample diameter is about, the whole diameter is 9 millimeters, and this total length, again, is equivalent to 6 millimeters. The thickness through which the X-ray is penetrating is approximately 2 millimeters. Okay, so the impactor here comes and impacts this particular cylinder. Again, the sample is flush with the epoxy mounted cylinder, as shown in this picture over here in B at the bottom here. And this on the right-hand side brass plate shows how the entire sample assembly is mounted. Okay, now there are 2 diagnostics that are being simultaneously used. One is that after impact, and everything is going to be timed such that X-rays are going to come through, penetrate through this 2 millimeter thickness, and give us 8 snapshots at different times of what's happening in the material as the shock propagates through the 6 millimeter length. Simultaneously, we are also putting a photodoppler velocimeter probe at the back of the sample, of the 6 millimeter length sample. Okay, and it's going to monitor a free surface velocity profile at the back of the sample. Again, that's a backup diagnostic that can come in handy. These are the 8 images that we captured from one of the experiments, and you can see this is at time 0 nanoseconds, 153 nanoseconds, 306 nanoseconds, and so on at essentially every 153 nanoseconds passed. What you are looking at is, again, remember, this is a 3-dimensional object. The X-ray is penetrating through a 2 millimeter thickness. So what each image is revealing, each image is revealing a 2-dimensional projection of a 3-dimensional object. Okay, and in 2 dimensions, we are still able to see some profile of the circularity of the particles. Okay, you can see this contrast. Okay, at 0 and 153 nanoseconds, and at 306 nanoseconds, you see the sharp line. Okay, that's the arrival of that shock front, and the contrast there is clear. It's very obvious. Okay, and you can see again at a later time, 459 nanoseconds, the shock front is propagated further. At 612 nanoseconds, again, it is propagated even further. And by the time you get to 765 nanoseconds, that shock front has propagated through that entire span of the field of view, which was approximately 2.2 millimeters of the sample that we are viewing, although the entire sample length is about 6 millimeters. Okay, and of course, at later times, we don't see that shock front. You do see the disturbance of the particles, as they are being disturbed behind that shock front. Okay, so these are the images that we captured. Now, what do we do with these images? So, for example, in one of the images, we can clearly see the shock front. These are at 4 different time frames for the experiment performed at 1221 meters per second. Okay. And you can see this front here. Okay. So what we did is, again, we identified 3 locations along the vertical span of that shock front at each of these 3 times. Okay. Again, at the 4th time, the shock front is past the sample. And by monitoring the time of travel and the distance of the displacement, we get the measure of the shock speed of the material. Okay. We also were able to identify the particle velocity by, if you see the circle that is drawn around that particle. So what we do is map the smallest diameter circle that confines a particle, okay, and monitor the location of the vertices of that circle. Okay, the displacement of the vertices at different times, that's what gives us the particle velocity. Okay, so that way, we are now able to go inside the material and monitor the shock and particle velocity. And if we do that, this gives you the table of all of the experiments that we did. This was a 3-day campaign, about 19 experiments. The different color codes indicating in the lettering are the different orientations. So for example, the 110 impact direction, or the 100 impact direction, or the 010 impact direction, okay? For the impact velocity for each of the experiments. And these 2 columns in green here identify the shock front thickness and the shock rise time. This is interesting. You know, even in this highly composite material, we find that the shock front is fairly narrow. It has a time scale of rise time of the order of 10 nanoseconds, okay? In a shock front thickness of about tens of micrometers, okay? And then the right 2 columns here are the measured parameters, the shock velocity and the particle velocity, okay? Again, these are parameters, I should emphasize, that are, again, the in-material parameters obtained from X-ray phase contrast imaging. And if I then plot all of the data, okay, this is all 19 experiments, plot the shock velocity as a function of particle velocity, okay? In a way, we are not seeing much of a difference, you know, in the trend that has been observed, considering the error bar, and the error bars are fairly still large, okay? But no obvious trend one way or the other that we can, convey here. At least it's indicating the material is not going through any physical or chemical change that would alter the density of the material, okay? But what about the orientation effect? Remember, we did impact experiments along different print orientations. So if I were to look at that individually, so these are the data points for the experiments performed with impact along the 100, that's the print direction. You can see the data points. Okay, the error bars are not indicated here because they were huge, and I think they mess up the overall plot here. Okay, but again, you can see the overall trend with the limited number of data points that we have for this orientation. If we consider the 010 orientation, again, we have 4 data points. You can see there's a slight deviation from the 100 orientation. And then when we come to the 110 orientation, again, we have 4 or 5 data points, okay? So what do we infer from this, okay? Is there an effect of orientation, okay? Now, I'm not showing you any of the error bars. And without the error bars, it seems like maybe there is a slight effect of the orientation. But if you put in the error bars, there would practically be no effect of the orientation. And I think in general, what we find is that really there is not much of an influence of the orientation, even though we observe the voids were aligned more along the print direction, okay? But turns out that because we are considering a small sample dimension, okay, a field of view which is 2 millimeters by 2 millimeters, within that scale or within that span, the anisotropy of the void orientation is very limited. And because of that, we are unable to see a clear influence of the effect of orientation associated with the impact direction relative to the print directionality as well for these AM manufactured materials. Okay, so what else can we do? Now, remember, I also mentioned that we performed Pdb analysis. Now, the Pdb analysis is performed on the back of the 6 millimeter long sample. The X-ray probing is done in the front 2 millimeter. Okay, so we are not monitoring the same location. Plus, the Pdb is capturing a volume average response of the overall material. So you would expect to see some difference. Okay, but the Pdb was done at least to make sure that the shock and particle velocity correlation that we obtain based on the X-ray phase contrast imaging is still within the limits of what would be reasonable. Okay, so let me show you. These are examples of the profiles that we capture at different impact velocities. And there's a lot of information that is captured in these. You know, one of the things that you see at this low velocity, 704 meters per second impact experiment, there is a hump here, a knee, before you reach the peak velocity. Okay, and that knee is indicative of some type of mechanical rubberization, meaning the composite material is becoming rubberized. Okay, and at these higher velocities, the velocity distributions that you observe at 948 and 1209 and 1762, as you increase the velocity, you get more and more of these velocity dispersions. We feel that these dispersions are because of the ejecta of the rubberized material, you know, that is shooting off at higher or at different velocities. Okay, so we are able to capture that. But nevertheless, for the sake of correlation, we're going to consider what that plateau or that peak velocity is in terms of how it represents that particle velocity, because the Pdb is giving you that back free surface velocity, which is correlated to the particle velocity. So if we were to plot the particle velocity obtained from the Pdb as a function of the particle velocity captured from XPCI, okay, the data points here show you how the two are correlated with each other. If there is a one-to-one correlation, then the dashed black line would give you the response, meaning the Pdb particle velocity, it matches exactly with what the XPCI particle velocity is. But what we are finding is that the XPCI particle velocity is actually slightly higher than what you measure with the Pdb. And that's again expected, because remember, Pdb is measuring the response at a longer distance, at about 6 millimeter distance, whereas the XPCI measuring a field of view that is on the front end in the 2 millimeter span of the sample. Okay, so it's possible that travel through 6 millimeters, the shock wave may be attenuating somewhat, and it is causing a slight decrease in the particle velocity. Otherwise, what we see is both particle velocity trends are giving us the same linear relationship, meaning the response of the shock and particle velocity measurement that we are making with the XPCI, I think is very much correct and in line with what you observe even with the Pdb. So it gives us a backing support that XPCI measurements are fairly reliable. Okay, now what about local effects? And that's one of the nice things with this. And this was by the way, I should mention, this is the first time that these type of correlations have been established with X-ray phase contrast imaging. So we can also do digital image correlation. Okay, this is a non-contact measurement technique for determining the strains. And all it requires is sequential series of images of an evolving body at different times. Okay. Typically, you have a speckle pattern that you intentionally deposit on the surface of a sample, or in heterogeneous materials, the heterogeneities itself can create that speckle pattern, and you can monitor the displacement of those features. Okay, and that's exactly what is happening. Okay, so you start, as is shown in the schematic here, you identify the image, divide it into subsets. okay, identify different subset regions, okay, before and after, at a certain time, monitor the displacement vector, okay, and once you have the displacement vector, the displacement can be translated into a velocity, and the velocity can then be converted into a strain field, okay. So this is again an example of what you would obtain as a normal strain epsilon yy, based on the displacement vectors that you would generate, okay. So based on our work, again, these are the 8 images from one of the experiments, okay. Once again, we can identify a certain region of interest, identify a subset, okay, and then track what's going on in terms of the, look at the displacement vector, convert the displacement vector to velocity, and then strain. So if this is a region of interest, okay, these 4 figures here are showing you the evolution of the normal strain epsilon xx. The color contours here are indicating the magnitude of the strain. Okay, the blue is very low, and of course the red is strain up to 20%. Okay, and what you're seeing is the strain front. I mean, literally, it's mapping the propagation of that shock front moving under conditions of uniaxial strain. Okay, and you can see that in this scenario, the only thing that you have is the normal strain epsilon xx. There is negligible lateral strain epsilon yy, and there's barely any shear strain as well. In fact, if we quantify these, you can see the results over here. In figure A, I'm showing you the strain variation, epsilon x component as a function of distance at different times. And as you see, as you go from 450 nanoseconds to 612 to 765 to 918 nanoseconds, you can see the maximum strain, the maximum normal strain component epsilon xs is about 20%. And over time, it's decreasing. Over distance, again, it's decreasing. What about epsilon yy? The lateral strain epsilon yy is negligible. By the way, notice the units here. The units for the normal strain epsilon xx are the absolute numbers here, and here for the epsilon yy, it's 10 raised to minus 2. So the strain that you get epsilon yy is literally negligible. Okay, same thing is with the shear strain component, epsilon xy over time in distance. This is again 10 raised to minus 2. So literally negligible strain. Okay. If you look at it in the context of what happens at different impact velocities and as a function of the print direction, this is for 100 print direction. This is perpendicular to the print direction. Notice what is happening here. This is again very interesting. The normal strain component epsilon xx at different impact condition reaches a peak anywhere from about 17% to about 22% at these 3 different impact velocities. Okay, and then of course, as a function of distance, it tapers down to 0. Okay, if you look at the 0-1-0 condition, okay, notice that the overall peak is still within that range. Okay, except for the 0-1-0 direction, there is lesser deviation in the strain. It's like literally between 20 to 22%, whereas in the 1-0-0 orientation, that maximum strain as a function of impact velocity ranges from about, let's say, 16% to about 24% or so, 20%. Okay, so there is some local strain effect being manifested by the orientation of the print, but otherwise, the equation of straight response, the bulk shock compression response, seems to be independent of the print orientation. Okay. Another measure of the success of the correlations here, I'm plotting here the longitudinal strain as a function of impact velocity, the DIC measurements, and then you can also use the USUP data that we generated. You can use the constitutive equations and convert those to the strains, okay, from that USUP data. And you see for the 1-0-0 in print condition, the two are, there are some difference, but not much in terms of the peak strain that they are measuring or they are monitoring. And then when you go to the 010 direction, as we saw in the previous picture as well, the deviation is much less. So the only difference, I think, in terms of the effect of print orientation is really coming from the local strain, but the bulk properties, the bulk shock compression response is essentially identical. Okay, so just to summarize, what I have informed you is, XPCI as an in-material diagnostic is being used to monitor the shock and particle velocities, yielding a linear equation of state, which is consistent with Pdb velocity measurements. The shock responses along different impact directions, so minimal differences. And I think, as I mentioned, these are due to the negligible directional porosity in the scale of the 2 millimeter span of the sample that is being monitored. Okay, the DIC analysis is a fairly reasonable method to be used here, even on the XPCI images, to monitor longitudinal strain variations. And again, there we see some difference, but not a whole lot. Okay, so finally, just to conclude that this is the first time that this XPCI technique has been used as an in-material measure of the shock and particle velocity, as well as the internal strain. Now, the fact that we did not see much of a difference or an effect of the orientation, we have done another series of experiments on samples with a greater amount of porosity as well as control porosity. So new set of samples was fabricated with collinear configuration as well as log cabin configuration. We've performed these experiments last fall, and these are still currently being analyzed. So I will have to get another opportunity to present the results of that. But otherwise, with that, I want to acknowledge all of the people that did this work and the funding from DITRA. And I, again, thank you all for your patience, and I'll be happy to answer any questions you may have.
Thanks a lot, Professor Thadhani, for that great talk. I learned a lot about shock-induced changes in materials, so that is great. Here we have Bruno, who is also one of our fellow organizers. So hey, Bruno has a question, so Bruno can go first.
Oh, thank you. I also learned a lot about shock compression testing.
Thank you.
Very helpful to understand how the technique works and how you validated the technique, and as a first step, obviously, to something much broader. So I have a background in materials, but for 3D printing applications.
Okay.
And so I'm really interested in sort of the broader picture, understanding where you headed with this in terms of, right, so we can engineer through 3D printing these different porosities, right, and then their directionalities. We can put architectures macro scale, we can go nanoscale if we wanted to, right? What is the overall sort of direction and impact that we're trying to have in this field?
Yeah. So the first thought was when I first saw the image of a cross section of a 3D printed material, that had a high density of solids inside it, with voids that have some orientation, but they are in random locations. Sizes are random, particle distributions are random. There are some nearest neighbor, and then there's some periodicity, there's some aperiodicity. Okay, it is a mess. Okay, so the first question was, does it matter? Okay, in terms of what will be the shock response? Okay, and when you ask that question, does it matter? Again, it's a very vague question, because then you have to confine yourself in terms of, well, does it matter in the context of what? Okay, not just the performance, but the scale over which I'm doing my experiment. If the scale of experiment is huge, then all of these porosities and the heterogeneities that were present there are definitely going to play a role. Okay. But if my scale of experimentation is tiny, where the heterogeneity level is, I think the material ended up being like a homogeneously or a highly homogeneous heterogeneous material. Okay. There are heterogeneities, but they are very homogeneously spread out, at least within the scale that we are investigating. Okay. So that was the first thing. Okay. That do these heterogeneities matter and at what scale? Once we understand that, then we can use 3D printing to tailor the types of heterogeneities we want, whether it's the location in the scale of the voids, the porosity, or the pattern in which the solid particles are going to be distributed. Okay, so I think maybe one thing I did not emphasize or briefly mention, the rise time that we measured in this material was like tens of nanoseconds. It almost behaves like a homogeneous material. Okay, but if the heterogeneities were really playing a role, and if I want them to play a role, then the shock rise time will be like hundreds of nanoseconds, which means I will have a lot of energy dissipation. Okay, so if the interest is in energy dissipation, I can structure the 3D printed material so that there will be a significant dispersion of the wave as it propagates, and you'll end up with energy dissipation. Or if you want focusing effects, then I can structure the particles and the voids so the shock wave will focus in certain directions. Okay, so that's the idea. Okay, that's the idea. Okay.
Thank you. I think that was very helpful.
Okay.
All right. So my colleague, Professor Shandit Day, is also on the call, and he has a question. Shandit, you can go ahead.
Professor Thadhani.
Yes, sir.
Quick question. Have you made measurements on some other kind of samples where there are phase transformations? The reason I'm asking this is, let's say you have the spatial distribution of different phases at the end of the day.
Yes.
Because different regions could be having, capacity to overcome the barrier to phase transformation. So would you have a distribution of phases as you go along that front?
Yeah, that's a very good question. And I think that is something that I would love to do. Okay. We have not done that using the synchrotron. Okay. Obviously, we have done a lot of phase transformation studies using the bulk diagnostics. Okay, an example that I talked to you about, the metallic glass. But just to give you an example of what I would be really curious to do, like even in this material, now in this particular material, all of the solids were inert. Okay, I don't expect any of the constituents to go through any phase change, at least under the pressures that we studied them. Okay, but what if we had those constituents where you would see a phase change? Then I would like to see not only the propagation of the shock front and the measurement of the shock and particle velocity, but also X-ray diffraction, okay, to monitor in real time or at that same time as the shock is propagating, how are the particles undergoing phase change? That's something that I would love to do. Okay, and I think that's what, I don't think we have that capability yet at DCS, but that's something that we are heading towards, where you can do the simultaneous phase contrast imaging as well as X-ray diffraction.
So let's say once you have done this experiment, probably you could do electron microscopy and chemical analysis in regions within your sample?
Yeah,
right?
Certainly. So there are two things with that. Okay, one is that all of these experiments are destructive. Okay, so nothing is recovered after the experiment is done. Okay, the experiment, the way the experiment is designed, remember, we want to control the propagation of a shock wave, so it's only one directional. Okay, it's uniaxial strain. And if we design the experiment in that manner, there is nothing to confine the sample, and it is going to just completely disintegrate.
Oh, okay.
Now, we have done a lot of other work where the intent is to actually recover the material. Okay, in which case we have to put solid confinements. Okay,
Mm.
but when you confine the material in a solid container, then you don't necessarily have a one-dimensional shockwave propagation. The shock will sort of bounce back and forth from the containment into the sample. So at the end of the day, you will not know, you may still be able to recover, do the microscopy, character X-ray diffraction, et cetera, and you can see the changes, but you will not know what caused the change to take place.
Let's say we have a pearlitic steel. We have a pearlitic steel, and this shock front just goes through the material. So what happens at the end of the day? What happens? So it's like failure analysis. You're trying to, let's say, using failure analysis.
Yeah, you can. Yeah, so you can do that. Okay, and we have done a lot of work on a variety of dual phase steels. Okay, and you're absolutely right. So you can do if you're looking at failure studies, fracture studies, then by all means you can recover the fractured material, and do microscopy, fractography on the material, and look at what's the nature of the fracture surface. Are you seeing ductile, brittle behavior? Are you seeing faceted structures? Are you seeing any banding because of the presence of martensite? Are you seeing any, even phase changes that are altering the fracture profile? Okay, because that would serve as a source of energy dissipation and inhibit fracture in that sense. Okay, so you're absolutely right. If that is the intent in terms of observing the fracture surface, like post-mortem fracture surface, and get an idea of the topology, the nature of the characteristics of the fracture surface, those are by all means easily doable, and we have done a lot of that as well.
All right. So thank you, Professor. We have another question from my colleague here in mechanical engineering, Professor Pedro Peralta. So Pedro, can you go ahead?
Hi, hello, Professor Thadhani. Thank you so much for.
Hi, Pedro. Yes, good to see you.
Very interesting talk.
Thank you.
Thanks for coming. It's great to see a fellow shocker.
I'll take that as a compliment.
And it is. So actually, two quick questions for you. Your Pdb probe, how big was it? I mean, actually, I was really interested on those macro measurements. Yes, but Pdb probes can be really sharp and can be very big. And actually, at DCS, I've been talking to them about what I call large field of view Pdb. I was curious how big was your probe?
I think these are, if I'm not mistaken, these are 100 micron probes.
Okay, all right. So that's pretty good. Yes, and actually appropriate for the the length scale of your material. Yes, so you'll get a bit more of an average.
That's correct. It's an average response. Yes, okay. And as I mentioned, it's way behind the sample, so the shock has to travel 6 millimeters, and by the time it gets to the back surface, it is somewhat dissipated.
Yes, and but it was nice to see that it was actually a nice plateau, though. I mean,
that's true.
It is still, I had the same thought. Yes, I mean, are you getting to a point where the 1D condition is actually degrading because you're back there?
Exactly.
But you are smack the middle. I think you're still probably there.
Yes, yeah. So it was more as a backup probe rather than a definite probe.
Okay, and the other question I had was on your DIC measurements, your strain profile, and it was actually very nice to see that uniaxial strain is working as it should.
Yes.
But I find that it was interesting to see that the strain gradient. I expected it to be a little sharp given what your XPCI looks like. Yes, I mean you see like a sharp change of contrast where the shock front is, but your strain gradient is larger than that. And I wonder if you could comment a little bit on what you think is happening in there.
Yeah, and I think in part, I feel that it's, what we are looking at is not necessarily a two-dimensional flat surface.
Great.
We are looking at a 2D projection of a 3D object. Okay. So I think some of it is being influenced. We don't know where in the plane, in the depth of that observation is the strain. So I think I would view that strain more still as a local strain rather than a macro scale strain observation. Okay.
All right. I mean, actually, I had similar thoughts. Yes, I was wondering about that because you are making this true thickness
Yes.
measurement,
Yeah.
and you're actually looking at the projections of all these particles
Exactly.
on
Exactly.
the PCI. So you're looking at them at different depths. Yes,
That is correct.
and you're looking at the shades and the DCI, the DIC, while it's great, might be tracking particles across different depths. Yes, and something of that sort. And
yes, yeah. So I think what it needs really is, and we were hoping that the CT images that we have captured, would give us, how a 2D projection looks like. Okay.
Yep.
But again, some of the particles, the melamine particles, again, those have no contrast. Again, they have the same density as the polymer matrix. Okay. So we were not really able to get. So essentially, we want to create, maybe even through simulations, how will this 2D projection of a 3D object look like? Okay. And I think if we have that one-to-one matching with with the images that we are capturing, I think then the DIC analysis will be much more robust.
That sounds great. I'm looking forward to that. So and thanks again for coming. That was great. Yes, and
Thank you.
You have
Pedro.
a good day.
Thank you. Good to see you. Yeah.
Yep.
Great. So Krishna has a question. Krishna, you can go ahead.
Yeah. I should probably articulate this better, but the relationship between the shock velocity and the particle velocity is linear, right? Is there a fundamental reason why it's linear? I mean,
no. So it's really, there's no physical, if you're asking, there's a physical scientific reason, there's no physical scientific reason. Okay. The shock and particle velocity just show an empirical, linear relationship, unless the material changes its state.
Yeah.
Okay.
Okay.
So it's a very convenient way to monitor the shock response of materials. Okay. By correlating the two parameters, and the two parameters are easy to measure as well.
Yes.
Okay. That's why they are conventionally used to do that.
Okay. So very quickly, and then you also had a nice plot with the particle velocity as measured by the phase contrast and by the Doppler
PDB,
right? And I mean, there was, of course, it's a nice linear relationship, but there was an offset, if I may. Would that offset change depending on the heterogeneity or the extent of heterogeneity as you proceed into the material? I mean, in fact, the point that I'm trying to make is, could I use that relationship to figure out the extent of microstructural heterogeneity or something of that material?
Yes, I think so. There are two aspects to that. Okay, one is that one can argue that because the shock is traveling, for the PDB measurement, shock is traveling a longer distance, 6 millimeters.
Yeah.
So maybe there are more heterogeneities along that 6 millimeter path. Okay, and that's why the measurement that you get from there is going to be different from what you get with the XPCI images, okay, which are monitoring only on the front end. Okay. Now, on the other hand, I think like what Pedro and I were talking about, the longer 6 millimeter span is also a distance over which the shock can actually dissipate.
Okay.
Okay.
Yeah.
And in fact, a signature or a marker of that, and maybe I forgot to mention that, if you look at the PDB profiles, the rise time from the PDB profiles is actually longer. It's
Okay.
100 nanoseconds.
Yeah, I think you mentioned that.
Okay, compared to the rise time that we measure in the XPCI images, meaning something is happening. The wave is slowing down somewhat.
Yeah.
It is becoming dispersed. I don't know if I should say slowing down, but definitely it is dispersing. Okay. Now, again, if the dispersion is an effect of the longer distance or the heterogeneity, I think it's a,
Okay.
it can go either way.
Can I just ask a very quick follow-up, Ankit?
Sure.
Sure, go ahead. Yeah.
So I mean, just a thought experiment. If I'm just taking single crystal metal, right, some nickel or something, and I'm looking at this relationship between the laser Doppler measured, I mean, the versus the phase contrast, would you see a difference as a function of length? Or, I mean, like what I'm trying to say is, if I'm removing the heterogeneities out of it.
Yes. So yeah, if it be a perfect material.
Yeah.
Okay. Even in a perfect material, as a shock wave traverses,
It will create its own.
it will create its own heterogeneities.
Yes. But there is, I mean, it's very interesting, rich physics there, right? I mean, in
Yes.
terms of, okay,
Absolutely.
in terms of just using that relationship, what is the multiplicative factor? And we can,
That's correct.
Okay.
Yeah. So the second batch of experiments that we have just done, there, the PDB is, the samples are shorter. So we are measuring the PDB right at the end of the 2 millimeter span.
Okay. Yeah.
Okay. And I think that hopefully will give us a little better feel.
Yeah, no, this is a very interesting simulation problem that we can tackle. Ankit, if you're interested.
Yes, I will have a chat with Professor Thadhani offline maybe sometime. Yeah. So I think we're running short of time. So I can ask one final question. So are there any, it's very similar to what Shanzip actually asked before. So do you have any plans currently to do similar studies on, say, paralytic kind of steel, or even strategic materials like titanium-based alloys, so to say? Do you think that's an interesting problem that would be worth addressing?
Yeah, so it depends what you're asking. We are looking at stainless steels, 3D printed stainless steels. Right now, we are working on it. We just submitted a manuscript to ACTA on 3D printed stainless steel. We are working on bimetallic materials. Both are, these bimetals are printed using 3D techniques. Okay. But all of those are utilizing the diagnostics that we have in our lab. Okay. We are not, so the nice thing at the X-ray, the dynamic compression sector using the synchrotron is literally like, what are the materials where you can best leverage the X-ray phase contrast imaging and X-ray diffraction? Okay. I think there you want samples that are going to have whatever heterogeneities that are going to be there at the scale of what you're going to be able to image. The X-ray penetration depth is 2 millimeters. Okay. So that sets you a certain limit. Okay. The width span is also about 2 millimeters. So whatever heterogeneity there is has to be within that window of the sample dimension. Okay. Now, as I mentioned earlier, I think it would be great if we were to study like a composite which has these particles that can undergo phase change. Okay. I think it would be ideal because then you can monitor both the X-ray diffraction showing the phase change as well as the phase contrast showing the propagation of the wave, the shock front.
All right. Yeah.
So I guess you're indirectly suggesting that given that the window is about, if I remember correctly, a few microns, right?
2 millimeter.
Okay, 2 millimeters. So you want to engineer heterogeneous that are sub-millimeter scale and find additive manufacturing processes that can deliver that.
That's correct. So the new batch of samples that we have made, the same material, we actually have done that. Okay. And we have done the experiments as well last fall. We are right now just analyzing all of the images, and we are seeing clear distinctions. Okay, but those materials still don't contain any components that go through phase changes. Okay.
So 1 millimeter is the upper bound, and in terms of pixel resolution, right? What would be the lower end of the bounds of scale? Let's say nanoporosity or microporosity.
Let me see. I think I had that. What is it? It's microns. It's
Tens of microns.
2.4 micron pixel. Okay.
Okay.
Yeah.
That's pretty good. Interesting. Thank you.
Yeah.
Thank you. Yeah. So Shandip has one final question. Shandip, you can go quickly and then we can.
Okay, thank you. Professor Thadhani, you
Yes,
showed us a picture of Flagstaff and the meteor.
Or the meteorite?
The meteor, no, yeah, I have, since you showed that, I have a question. Like, you have this technique. Is there any way to study, let's say, high entropy alloys? So let's say
Yes.
this wave front goes through, maybe you could make some high entropy alloys, the effect of configurational entropy on this system. Like, how does the configurational entropy might change as the shockwave passes by? And then you have a new area of study. Like,
Yes.
thinking out of the box.
Yes, certainly. And I mean, that's what our interest is, even with the phase transformations. Okay. So any type of physical, chemical change that you get, I mean, my whole interest in the metallic glasses is that, I want to make, complex crystalline alloys, or actually composites, where part of the material, part of the amorphous material has been crystallized due to the propagation of the shockwave. Okay. Now, the question, if you ask me, can I control that?
Yeah, that's another story.
I'm not sure yet. Okay.
Yeah, especially on a sample larger than 2 millimeters, right?
So this was only for the experiments that are being done at the dynamic compression sector. Okay. I mean, the experiments we do in our lab, we can go with samples that are like almost 3-inch diameter by about few millimeters in thickness. Okay. Or if you go a little bit north of where you are, northeast of where you are to New Mexico, maybe you can do some explosive testing on a much more larger scale.
Mm-hmm.
All right.
Thank you.
Yep.
Thank you.
All right. Yeah. So I think we are about time. So we should thank again our speaker. Thanks for accepting an invite. It was a great talk.
Thank you.
Yeah, and we're glad to have you here. And yeah, Christina, any parting words?
Have a good weekend, everybody, and thank you so much for this talk.
All right.
Yeah, Christina, I mean, just looking at you, it makes me shiver.
Oh, I'm so cold. I had to get a blanket.
I know. Thanks, Professor Thadhani.
Thank you, everyone.
Thank you. Thank you very
We'll
much.
reach out to you soon offline to further.
Okay, sure.
Bye.
All right.
Bye-bye.
Thank you.
Christina, I hope
Bye-bye,
you feel better soon. Okay.
Thank
Bye-bye,
you so
everybody.
much. I hope so too. Stay safe, everybody.
Thank you.
Bye-bye.
Bye.
Bye.